This is Shelby from ARM, and I'll be giving a tutorial on CoAP, the Constrained Application Protocol, we like to call the Web of Things protocol. First, we should look at what CoAP is for. What's the problem we're trying to solve? In the old days of what we called machine-to-machine or M2M communications, it was really about building silos of devices hooked into their own services over the internet, but still using a lot of proprietary, hard-coded technologies. This was slow to develop, very hard to maintain. Think of it a little bit like the days of AOL and CompuServe on the internet. Anybody remember those? M2M is very much like that. What we're doing with the Internet of Things is very different. We're trying to really break down M2M silos and create things that can easily be connected into services. Many services to many things. And instead of just using the internet as a pipe for data, we actually use the web technologies, standards to connect devices and services together. So we like to think about things connected to services over the web. That's the problem we're trying to solve. And that's where CoAP comes in. Now, CoAP, the Constrained Application Protocol, is an open IETF standard. We created the standard in order to really extend web technology down to the unique requirements we see for small, constrained embedded devices on low power, low bandwidth networks. What that really means is that we can use a lot of the same paradigms and terminologies and techniques that we're familiar with from the web using HTTP with the Internet of Things. Some of the features of CoAP include a very compact 4-byte header. Typical bindings are to UDP. We also see bindings to SMS over cellular networks and even over TCP. CoAP includes strong security built into the protocol using DTLS. And unlike HTTP, the protocol is completely asynchronous thanks to the use of UDP. So we can build in things like subscriptions natively, do discovery, and even handle things like multicast requests. So CoAP's an interesting mix of making the web very efficient and adding features that are important for IoT applications like subscription and discovery. So what does it look like when we go from the web to a very constrained network or device? Well, of course, if we look at a typical web stack, we're looking at IPv4, IPv6, a TCP TLS transport, HTTP, and typically pretty verbose web representation formats such as XML or JSON. This can be thousands of bytes. When we work with a compatible but efficient protocol like CoAP for the web, we can actually, through a simple proxy, convert that down to something that is pretty efficient, hundreds of bytes, will work over any kind of IoT backhaul or Wi-Fi, cellular, and using a combination of IP, DTLS instead of TLS, with some optimizations from standards, CoAP, and very simple binary representations, we can really gain some efficiency. Now, if we look at really constrained networks, we start to see technologies like 6LoWPAN, which is just a stateless compression for IPv6 for 15.4, Bluetooth Low Energy, or other low power networks. When we have a network like that, the bandwidth and the frame sizes are very limited. So combining that technology with CoAP, we can get overheads down to just tens of bytes. And that's something we can carry in any technology that's out there today. So we can go all the way from very constrained embedded devices, networks, all the way up to the big web in one continuous set of technologies. CoAP, of course, is one key piece of the standards puzzle. It's not enough to just have a protocol in order to build an M2M or an IoT system that's not a silo. You need other standards around CoAP, for example, resource directories for registration, advice on REST interfaces that you can use with CoAP. We do those things in the IETF core. More so, you need the networks, you need the improvements in security, and you need things like device management. OMA Lightweight M2M is an example of device management, uses the CoAP as a basis for the standard, and the actual data objects, so the semantics that you use with CoAP. And those come from places like the IPSO Alliance or Zigbee, where we work on semantics for IoT. Now, to really understand how CoAP works and how you use a protocol like this for IoT, I think we should first look at how does the web work, how does REST work, because then you really see the similarities between how we do things on the web and how we do things on the Internet of Things. And the web architecture is really unique for a few reasons. First of all, it's stateless, so a lot of what we can build in the interactions between a server and a client, so in this case a web server and a browser, we can redirect that, we can use proxies in between, load balancers, we can do a lot of things to actually make the infrastructure scale. And that's a really important aspect of web architecture when we go and look at how do we need to make IoT systems scale, because actually there's a lot more devices out there than there are web browsers. The web architecture is also unique in the way that you can build standard interfaces using what we call REST. We'll talk a little bit more about REST in a moment. Naming on the web has something very standard, and we call them URIs. So we use URIs in order to identify where things are on the internet. And very common, HTTP, this is what you see in the URI bar of your browser. That tells you the protocol, in this case is HTTP, the authority, so where is that on the internet, what's the IP address, the port, and then you use things like paths and query strings. That identifies a resource, and that's a resource that you can then manipulate. You can get it, you can update it with put, or you can even add new things to it with post, or remove it with delete. That's really what REST is about. It's about identifying resources using a URI and then being able to get and modify representations of that resource. On the internet, when we resolve one of these URIs, we break it into its pieces, and these belong to different parts of the stack. So most of the beginning of a URI is the IP address that the IP stack uses, the port used by the transport protocol, TCP or UDP. We use DNS to resolve some of this. And the pieces that really belong to the application layer are, well, of course, the scheme tells us what kind of protocol is used. Here it's HTTP. With CoAP, it's simply CoAP, C-O-A-P, : //. The path and the query string, they belong to that application. They actually identify what resources are being exposed by that protocol on that endpoint on the internet. So the URI is very important. It tells us everything we need to know to access a resource. Now, in traditional HTTP, we have a complete client-server model, and it's connection-oriented. So if you want to make a request between an HTTP client and an HTTP server, well, you first need to set up a TCP handshake, three-way handshake. Once that handshake is up and you have a connection, you can send an HTTP GET, for example, with a URI to the server, and you'll get a response. So it's very synchronous, it's client-server based. Once you're done with that or a series of requests, you'll tear down the TCP connection. Typically it's a two-way termination, and then you're done. The problem with HTTP is, well, a few things. First of all, being connection-oriented, it's not all that efficient if you just want to send one simple piece of information. Connections also cause problems with the synchronous. If you want to, in both directions, exchange information at different times, it's difficult to do with HTTP because you need to keep open a connection, and quite often the client's not able to deal with incoming requests or unexpected responses. So HTTP traditionally isn't very flexible for IoT applications. Now, there's a couple different ways that HTTP can be used for communications on the web. And the two that people are most familiar with are REST, which we explained a little bit earlier, and something called SOAP, which is really about carrying remote procedure calls over HTTP. We're going to focus on REST here because that's what we found to be most efficient when we talk about simple devices and simple interfaces for IoT. And the reason for that is REST really uses the built-in features of the protocol, in this case HTTP and CoAP, to simply carry around the raw data that's needed, identify it using the built-in URI, and then manipulate it using the built-in methods. So there's really nothing wasted in REST. REST uses what the protocol has and nothing more, and the payloads we work with are usually very simple. SOAP is great when you're trying to build business logic together in business systems on backends. And what it's doing there is really encapsulating in XML remote procedure calls. So it's really calling code functions over a network rather than a standard network interface using the protocol. So we haven't found SOAP very useful for IoT over these web protocols, and we'll talk about REST for the rest of this tutorial. Now, a simple example of a REST request, doesn't matter is this HTTP or CoAP, is a server. In this case, the server is actually what has the resource, and this server has a resource called /temperature. And a client, in this case, somebody that's interested in getting the temperature from this sensor device. And for that client to actually get that data, it will simply do a get on /temperature. /temperature is associated inside the device with some code, doesn't matter how it's implemented, with a temperature sensor which has a representation in centigrade. And in this case, the representation is very simple. It's a text string of 22.5 C. As a response to that request, the server simply sends back a 200 OK. It marks the media type of the representation. In this case, it's application text, and the payload, 22.5 C. So very simple. It's a client get and a response with a representation of that resource. So that's a REST paradigm request. Now let's talk about the constrained application protocol and how it reuses REST, what it's useful for, and how it works. So when CoAP was designed, it was designed not just as a compression or extension of HTTP. In fact, it's really neither. What CoAP is a clean design of an IoT protocol where one of the requirements is the ability to support the REST paradigm, not HTTP as a protocol, and the ease of mapping to HTTP. So it's very easy to create a proxy that maps between CoAP and HTTP because they use the same semantics. But there are many more requirements that were required for a protocol like CoAP. Things like operation on a very constrained network, sometimes just kilobits per second in bandwidth available. The ability to do built-in resource discovery rather than depending on some third-party mechanisms. Support for sleeping devices, very small amounts of flash and RAM, multicast requests, very low latency over systems, built-in reliability, even though we're using UDP, subscriptions and notifications. So a lot of very interesting requirements that were put into the design of the protocol. The architecture, pretty straightforward. You can use CoAP peer-to-peer between devices. You can use CoAP between a device and a service on the internet, or you can proxy somewhere on the edge between a device and a service and use HTTP for part of the interaction. So just to recap, what is CoAP and what is not really? Well, it is a very efficient REST protocol, ideal for constrained devices and networks, very specialized for M2M or IoT style applications, easy to proxy back and forth from HTTP. But remember, CoAP isn't a general replacement for HTTP. It's not a compression. So it's not something you'd want to use, I want to get more bandwidth out of HTTP for use on a web page. Let's use CoAP to do that. That wouldn't be very useful because CoAP doesn't support all of the features that HTTP does. So it's not a complete replacement for HTTP. CoAP's also not restricted just to automation networks. We see the use of CoAP over the internet as a whole when talking to constrained devices. So there's no requirement to proxy CoAP at the very edge of the network. We see a lot of CoAP all the way back to the cloud. Let's look a little bit deeper at features in CoAP. Well, first of all, CoAP does have a scheme, CoAP://, or with security, it's CoAP S://. So we have a well-known port, for both of those. So whenever you see that scheme, you know what port 5683 or 5684, that you're going to request when you're talking to that endpoint. The UDP binding includes its own reliability. Touched on that briefly. That's a simple binary exponential backoff. So CoAP includes a very simple mechanism built in to do that. It's not replacing the features of TCP. So it doesn't have flow control. It's not trying to maximize the amount of bandwidth that can be sent over the network. It's simply send one packet, wait for the response. If the response doesn't come, back off, do it again. But you can only have one such request open at the same time. It's what we call nstart equals 1. And that makes sure that you don't overflow or flood a network. CoAP supports all the basic methods of HTTP, get, post, put, delete, supports URIs, but it does it in a very small binary header with options. And we'll look at the structure of that in a moment. A couple of the most interesting things, though, is that we can use MIME types with CoAP just like we can with HTTP. Very important for supporting standards over the protocol. Without the ability to indicate what kind of payload is there, it's very hard to go and parse and know what the information in the packet's about. Built-in discovery is very important. We'll look at how that works. And finally, the ability to do subscriptions and even do block transfers of larger files. In CoAP, we can think about CoAP as having really a request-response structure in the protocol along with a message structure. That is bound to DTLS in the case of UDP for security. If we use TCP, it's bound to TLS. And in cases of cellular, you can even bind it to SMS. The base messages simply make sure that a message is acknowledged with the right message ID. That's what's used for reliability. There are a couple types of messages. One is called confirmable. That's something that indicates reliability is wanted. And something called non-confirmable, which are really one-way, less reliable requests. Those messages are answered either by an acknowledgement in the case of a confirmable, or if there's something wrong with the request, it's not understood, a reset message can be sent. On top of that, the headers actually carry the real REST request response semantics. So the method, the response code, the options, which might be a URI, a content type, etc. That's where REST comes into the protocol. All those things are carried in a very simple header. The CoAP header is a 4-byte header, includes the version information, type of message, the REST code, which is either a request or a response. Something important to understand is that same header is used for both requests and responses. So there's not different headers for doing a GET and a different header for doing an ACK. It's always the same structure. So that makes a parser or a builder very simple. Messages always have a message ID that matches the particular message with the acknowledgement. There is an optional token. The token helps us match a request to a response, and in the case of subscriptions, it helps us match a subscription to all the notifications that come afterwards. Finally, there is options, and options are things like the URI of the request, if any, the content type, more complex things like if match. For example, if you're looking for an e-tag in a device. So more sophisticated REST requests, we can include those and encode them in options. And options are simply type length value binary options. They're short, they're easy to parse. So the option format shown here. So it deals with what we call deltas. So those are the differences between this option type and the next. And the length, and then the number of bytes in the option. And each option has its own meaning, and those are defined in the CoAP specification, and there's a registry for defining new options. So new options can be defined without actually changing the protocol specification. Here's a list of some of the options that are included in the base specification. So as an example, E-tag is used to see if the representation is the same as it was previously. URIs are split into parts. So if you include a URI, you include typically just the URI path, optionally URI query components, and less commonly the host and port parts. Those are special cases. Let's look at a request example. Here we have a CoAP client making a request to a CoAP server for a resource/lite. And this is a GET request, so the client's expecting to receive a resource representation back. So it makes a confirmable request. The message ID is included. That's 0xAF5 in this case. That request is encoded, sent to the server. The server responds with what we call a piggyback response. The response is sent right away. It didn't have to wait for anything. And that's sent back in an ACK message. The message ID must match. The code is a 205 content, so that means this is okay and there's content. And then the payload is simply included at the end of the message as a payload. In this case, it might be a simple XML structure. Typically, it would be a binary value. Now, what if we have packet loss? Okay, this case, the CoAP client sends a message, it's lost, server never gets it. There's a timeout associated with sending a confirmable request in CoAP. That timeout triggers, the client repeats the request, and this is very important, the message ID stays the same. That way we can detect duplicates. The client will double its timeout, so if this happens again, it takes a longer time. That's the exponential backoff. And finally, the ACK is sent. Servers can also send what we call separate responses. So if they have to do something that takes more time, let's say making a light measurement actually happens on demand, and it requires a long time to adjust to the amount of light, calculate things. The server can simply respond with what we call an empty ACK. Just ACKs the message. It doesn't actually give a REST response. The server is able to later send a separate, what we call a separate response. And this matches the token of the message because the response is coming at a later time. And it's its own message, so it's another confirmable in the other direction. So tokens are important for matching these things. This is simply an example of the bits and bytes that go into a CoAP message, what the pieces mean. These are very easy to parse. For example, the GET field is simply a 1 to indicate GET. The message ID is simply the ID number. And then this has an option which tells us the URI is temp. We never include the slash in the URI option itself. And in the response, it's similar. The same code field is used now to indicate a 205. That's code in decimal of 69. The same message ID, and then simply the value. Now, just like HTTP on the web, it's possible to cache CoAP. And it's a simple caching model. Cacheability is determined by a response code. That's a little bit different than in HTTP. And options indicate how the cache key is built. And this would typically be done in, for example, a CoAP to CoAP proxy, and you want to improve the energy efficiency, the scalability of the devices. You try to cache in between. It could also be done at a CoAP HTTP proxy, where you want to basically protect the constrained devices from much more capable HTTP servers on the web, which could very well drain the battery on a constrained device. And a proxy might look like this. For example, an HTTP client making an HTTP GET to /lite would just be converted to a CoAP GET, and vice versa, the response comes back. That can be cached. We have cache rules. In this case, the max age is set to 30. That means that light representation can be kept for up to 30 seconds. If a request comes within that time, in this case, an HTTP GET to the same resource, if the cache is still fresh, we can simply send the response back from the proxy. We don't have to bother the CoAP server. Now, CoAP includes the concept of subscription built into the protocol. And this is something very interesting because this was always missing from HTTP, and it's been done in about 300 different ways over HTTP, different mechanisms for doing subscription. In CoAP, there's one way to do this, and that makes it great for interoperability. To make a subscription, it's really very simple. You simply do what we call a get with observe. So there's a special option called observe, and that tells the server that, okay, this is not just a normal get. This is a get where this client wants to get every update that I make to this representation. It's up to the server what an update means, how often that update happens, but the client wants to know if this representation changes. Subscriptions should include, or observations should include tokens. A token lets the client separate this observation from others. There could be multiple at the same time. And every time that representation changes, the server simply sends a new value, a new response to the client. And that response keeps happening every time the representation changes. This is an example of two different notifications. Important thing to notice here is that the token always matches. Likewise, if we want to transfer larger representations, UDP, typically we're limited to a 1500 byte MTU. UDP can only include so much information in each packet. Unlike TCP, it's not a stream. Most of the time, that's fine. Sensor data is very small. We're typically in tens of bytes or hundreds of bytes. But sometimes we have a log file or a firmware, for example. In that case, we want to break that down. That's built into CoAP as well, something called core block transfer, where we can get a light resource and be act back with a response that says, okay, here's a representation, but this is only a block of the representation. And the client needs to go through those blocks and keep requesting the next block. So it's a manual mechanism to run through the pieces of a representation. Also very stateless. So how do we get started with CoAP? Well, the great thing about an open standard is that we have a lot of open implementations out there. Examples include Embed from ARM, where we have CoAP support built into the SDK. There are great Java libraries, for example, Californium, C libraries like Erbium. These are in the Eclipse Foundation. We have libcoap, jcoap, opencoap, and several OSs with support just built in. So it's pretty easy to get a hold of an implementation or even implement one yourself. CoAP is a pretty simple protocol, easy to get started. You want to think through if you want to make a commercial grade implementation, of course. CoAP is also part of many commercial products and systems. So CoAP is shipping in a lot of products today in systems from street lighting to smart metering to asset tracking and things we've never even heard of. Couple examples are, for example, at ARM, the ARM Sensino products include CoAP in all of the different components. We have Wi-Fi modules like the RTX 4100 that actually include CoAP out of the box. Firefox has a CoAP plugin called Copper. Wireshark has CoAP support built in. So it's a pretty rich ecosystem of protocol support across the board. Now, what about discovery and semantics? How does that work? Well, first, to understand discovery, we need to understand something called web linking, because this is what's used as a basis for this in IETF core. So links have been around for a long time. Something called web linking really formalizes this, defines what we call relations or typed links. So HTML and Atom have forever allowed you to link things. That's how HTML and HTTP work together on the web. You click a link, the link brings you to a new place. When you add relations to links, it lets you also describe the relationships between those resources. So this next URI is actually the next chapter of this book. It's not just a random URI, it actually means something. This web linking framework is standardized in RFC 5988 in the IETF. So that really unifies HTML and Atom links, describes them in the same way, and has a registry for relation types. Links have different kinds of serialization. So I mentioned a couple. There's also one that's actually built into HTTP. It's called the HTTP link header, and it defines a format for representing links. This is an example of what an HTTP link header might look like. Here it includes a simple text-based URI, a relation type, a title. There can be different attributes attached to it. Now, how does resource discovery work in general? Well, first we should understand what it's really about. Now, some people talk about service discovery. Well, service discovery is when you don't even know what services are available or what protocols they use in the first place. So examples of this are MDNS, DNSSD are typically used for that purpose. When we're on the web, that's not usually the case. When we're using a HTTP protocol with a browser or we're using CoAP, we typically know that we're looking for web resources. So we don't need to know what protocol we're looking for in the first place. What we really want to know is what are the URIs associated with resources we're looking for? And that's what we call resource discovery. In core, we've actually built this into the protocol. So there is a well-known resource that's been defined to actually discover any endpoint's resources. Those resources are represented in what we call the core link format. And that's simply a compatible format with the HTTP link header from web linking. So we've actually reused web linking from the web world for the purpose of discovery in CoAP. The core link format and the different attributes associated with IoT type resources is defined in RFC 6690. So that defines the serialization in a formal way. It defines the well-known resource, which is /.wellknown/core. And that resource is globally reserved for this one purpose, not only in CoAP, but in HTTP as well. So this resource discovery mechanism can be used with HTTP, which is pretty interesting. When you do a get to that resource on any endpoint in the world, as long as there's no security reason why it wouldn't be returned, you would return a resource with links. And those links point to the resources available on your endpoint. And this is an example. So a CoAP client wants to know what this particular server has available. It simply sends a GET request to /.wellknown/core, and that server will respond with content, and that content is simply a list of links. It's a simple text format. So for example, it has on /dev/bat, it has an IPSO application framework battery value available. And we know that because we've actually built in semantics, what we call a resource type, into the link format. So we actually can semantically know that, okay, this has to do with IPSO dev battery, and that's defined in the specification for resource types. These can even be registered. We also know that there's a content type of 0, that's text plain, and that the resource is observable, so we can actually subscribe to it. So we can get a lot of semantics out of these links that we get out of a simple device. They're easy to parse, they're easy to create, they're static. So all around, very simple to use for IoT. Now, it doesn't always make sense to do peer-to-peer discovery. You don't always know if this device is in the same network. You might not even know where it is on the internet. And it might not be in a reasonable scope that you could even do a multicast discovery. So for many systems, it makes sense to use a centralized, what we call a resource directory, where endpoints that have links can register those links with a directory, and clients that are looking for resources can discover them, get the URI, and then directly interact with that resource. So it's not a middleware, it's not a proxy, it's really just a directory of links. Think of it like a reverse search engine. If you look at search engines on the web today, they will go and crawl the web looking for resources. They'll collect the links, some descriptions and metadata, and they'll display the links for you, the user in the browser, to go and follow them. Resource directories are working in the same way, except instead of going out and crawling the web, they wait for the endpoints to come to them and actually tell them about themselves. Resource directories work in a pretty simple fashion. Those registrations are simply posts with links to the resource directory. Could use the core link format or any other link format. Nodes use puts to update the resource directory periodically. And then lookups can be made, either using CoAP or using HTTP. So lookups could be from constrained clients or they could be from very full functional web applications. Resource directories have a whole range of applications. And we'll see one a little bit later in the OMA lightweight M2M standard, which uses a resource directory. Here's an example of what a registration to a resource directory might look like. You could post some links to a resource directory. An application could look those up, and then you could update your links. You could remove your links. There's many nice interfaces that you can create and use around a directory. Now let's go back to the semantics again. So what if you want to make a real application? What if you want to make an application that can use devices that weren't just designed in a silo? You need to be able to have meaningful names for resources. You need to define what those names could be. You need to have well-known REST interfaces for those things. We actually have recommendations on how to use these mechanisms we've designed into core link format. There's a draft about this called Core Interfaces in the IETF. There's also a recommendation on how to use the web application description language, even to define those REST interfaces. So those use different fields of the link format in order to indicate what those semantics are. You also need a format. So just having the semantics and the REST interface isn't enough. You want to say, what is the format of this payload? And luckily that means that we use the media types of CoAP. Very easy. Define the media type, you can use it. And those might be industry-specific things. They might be markups that are like OBIX, SensorML, EEML. There's many of these that have been defined. We have a few standards too. SenML is a good example from the IETF. Standard way of packaging up sensor information that can be serialized as XML, as JSON, as CBOR. CBOR is a standard binary JSON format, RFC 7049 from the IETF. You can use to make very compact representations. We also have some bigger standards around CoAP and the use of semantics and media types. And one good example is the OMA lightweight M2M standard. We'll have a separate tutorial on that, but that really defines the way you can use CoAP to access what are called objects. It's a standard data structure that can be used to define just about any kind of object, how to do device management, how to interact and register using the resource directory, how to manage security. So it's really a whole system standard. The IPSO Alliance are defining, compatible with that standard, what's called IPSO objects, so the actual application semantics for use with OMA over CoAP. This is a good example of the kinds of semantics that are already defined. These are kind of general purpose things that any REST interface might use on a device. And this is from the core interfaces specification. So these define simple interface types. It could be reused. For example, a sensor, which has a method get. So it defines a reusable interface type. Any kind of sensor could use this interface type and then define what kind of sensor it is and what kind of value. Could be a parameter, a read-only parameter, an actuator, and it defines things like bindings and batch formats, links. So you can really build and rebuild and reuse these interfaces to build different kinds of sensors and actuators. So this is a recommendation for REST interfaces. That's the end. Thank you for listening to the CoAP tutorial, and welcome back for other tutorials.